Okay, we are going to discuss about equilibrium and Q value, and then equilibrium and Le Chatelier's principle. So let me first go over equilibrium and Q value. I'll first define what Q value is, and then I'll explain, based on Q value, how we can predict the direction of a chemical reaction. So let me write down the topic. Okay, I'll explain that with this example. 2H2 plus O2 giving 2H2O. And let's assume that I have hydrogen concentration of 1.00 molar, oxygen concentration of 1.00 molar, and water concentration, these are all gas phase, 2.00 moles per liter. Now the question is, with these concentrations, is it going to be in equilibrium? I give you a Kc value, which is the equilibrium constant value, equals to 3. In order to know whether it's in equilibrium or not, first we need to set up an expression for Q value. So Q would be defined exactly like equilibrium constant. Product concentrations on the top, reactant concentrations on the bottom, raised to the power coefficient of balanced reaction. So in this case it's going to be H2O raised to the power 2, hydrogen raised to the power 2, oxygen raised to the power 1. Now then, what is the difference between Q value and equilibrium constant? In case of equilibrium, these would have equilibrium concentrations. So Q value can have any concentration, and every concentration is not equilibrium concentration. Equilibrium concentration is the one that you get at the end, after equilibrium is reached. So let's first find out whether these represent equilibrium concentration or not. So let's plug in these numbers. If these represent equilibrium concentrations, then my equilibrium, the Q value, which would become Kc, which would be 3. So in other words, these concentrations, when these are not equilibrium concentrations, they would keep on changing until it reaches equilibrium. When it reaches equilibrium, this ratio is be equal to equilibrium constant. So let's now test that. Now H2O squared, this 2 is squared. Hydrogen is 1, so 1 is squared, time, oxygen also has the value of 1. So this is 4. So Q value, this is the Q value, is greater than Kc. That means my Q value is now greater than equilibrium constant. If these were in equilibrium, this would be equal to 3. So obviously it is not in equilibrium, and these concentrations are not equilibrium concentrations. So here we know that these concentrations do not represent equilibrium concentrations, as this Q value is not equal to equilibrium constant. Rather, it's greater than equilibrium constant. Next question is, if it is greater than equilibrium constant, how it is going to change? Q value is going to change with time, and which direction of reaction will be favored? Now normally reaction would happen both ways, and we'll go over this. When Q is greater than Kc, that means Q value has to go down. It has to reach value of 3, then there will be no more changes. That every reaction is like that. You can begin with any concentration you like. When your Q value is greater than Kc, then Q value will keep on decreasing. If Q value is less than equilibrium constant, then Q value will keep on rising until it gets equal to equilibrium constant value. Okay, so in this case we know that Q must decrease because it has a greater value, must decrease. because eventually every reaction is going to reach equilibrium. So Q value must decrease. Now, mathematically we know that when Q decreases, that means the stop number is going to decrease. So Q decrease means H2O concentration decreases. It decreases more than the bottom numbers. Now what does that mean? H2O decreases means reaction can happen both ways, left to the right or right to the left. Whatever amount of H2O you have at any point, if I'm saying that it's going to decrease with time, that means the reaction along this direction would be favored. Because by going from right to the left, some of this water would break down into H2NO2. So in this case, direction of reaction that would be favored would be from right hand side to the left hand side. If this were in equilibrium, neither direction would be favored because you'd have two double arrows, equal and opposite. But since this is not in equilibrium, Q value is greater than Kc, that's why one direction would be favored over the other. And this would keep on happening until it reaches equilibrium. Okay, so in this case, right to the left would be favored. Say, for example, in a problem I have Q value less than equilibrium constant. Then Q value would increase. Q value increasing means product value would increase. And product value increases only when reaction is favored from reactant side to the product side, or left to the right. So keep that in mind before I go over another problem. The next problem that I would like to go over would involve equilibrium concentration calculation. So this would be equilibrium concentration calculation. Two NO gas giving N2 gas plus O2 gas. Say Kc is given, Kc equals to 16.0. And we need to know what is the equilibrium concentration of NO, nitrogen, and also oxygen. Let's do this problem. We also need to know the initial concentration of NO, which we forgot to write down. Initial NO is also given 1.0 molar. So let me repeat the given information. Due to the reaction we are looking at, initial concentration of NO is 1.0 molar. Kc value is 16. I need to know equilibrium concentrations of NO, N2, and O2. Equilibrium concentration is the concentration that you get when equilibrium is reached. Now let's work on this problem. Initial concentration of NO is given, but there was no mention about nitrogen and oxygen. So we can assume that initially there was no nitrogen and there was no oxygen. Okay, so keep that in mind. At equilibrium, as reaction happens, a part of this NO is going to react. And at this time, we don't know how much. So at equilibrium, let's assume that X is the quantity that reacts. So then equilibrium value will be given by 1.0 minus X. Let me repeat this. This was the initial concentration. As reaction goes on, a part of this NO is going to react and is going to make N2NO2. Since we don't know how much is breaking down, so let's assume it's X. So X of NO is going to react, and that's why leftover is going to be 1.0 minus X. And that's going to be the equilibrium concentration for NO. Now when X of NO breaks down, we need to know how much of N2 is being formed and how much O2 will be formed. This is how it works. When 2NO breaks down, you get 1 N2 and 1 O2. This ratio has to be maintained. That means if X of NO is breaking down, half of N2 will be formed. So it will be X over 2, and half of oxygen is going to form. Now why is half? Because these numbers are 2, 1, 1. Chemical reaction tells us what is being used up and how much of the product we are going to get if that amount is used up. Like 2NO when used up, you get half of that quantity, which is 1, of nitrogen formed, and half of that quantity, which is 2, half of that would be 1, of oxygen formed. So when X breaks down, you get X over 2 here, X over 2 here. So now I can write down an equilibrium expression. So I can write down, say, Kc equals to N2 over O2 at equilibrium. This is a raised to the power 1, and NO at equilibrium. So let's put down EQ as at the bottom, and this is going to be a square. So this coefficient becomes square. Coefficient is 1 raised to the power 1. So this is 1, 1, and this is 2. Now I have X over 2 plus 0. That's X over 2. So total equilibrium value will be 0 plus X over 2, which is basically X over 2, times, for the oxygen, again 0 plus X over 2 is X over 2. And at the bottom you have 1.0 minus X. After you understand this, try to redo this problem without looking at how I did it. That would be a very good practice. Homework has similar problems. You can also try them. Now Kc equals to 16. So 16 equals to X over 2 whole squared by 1.0 minus X squared. From here we can write down, take the square root of it. You know that when you take a square root, you get two values, pluses and minuses. We deal with all pluses because concentration has to be positive. So only take plus 4 equals to X over 2 divided by 1.0 minus X. We took a square root on both sides. Now if you solve for X, this is the value you're going to get. 0.89. So what happened to this quantity? This is the quantity of NO that broke down or that reacted. So what is the equilibrium concentration of NO? So NO at equilibrium would be given by initial value that we had, 1.0, minus the quantity that broke down, 0.89, that we just calculated. And the leftover is going to be the equilibrium concentration, and which is 0.11. Okay, so we got our answer without any problem. Now, what about N2 concentration at equilibrium? 0 plus X over 2, which is X over 2. So, and we already know the X value, which is 0.89. So it's basically half of 0.89. Similarly, for oxygen, value at equilibrium is going to be half of 0.89 because that's also X over 2. So we got all these equilibrium concentration values. And make sure you understand every step of these calculations. The next problem that I'd like to go over would apply what we call Le Chatelier's principle. Okay, so it's going to be Le Chatelier's principle and equilibrium. Le Chatelier's principle is defined several different ways. In different books you find these definitions, but they're the same thing. One definition I like the best says that when stress is applied to a system in equilibrium, changes will happen so as to relieve the stress and restore a new equilibrium. So what is the stress in a chemical reaction, and how can it get rid of that stress? So that's what we're going to explain on the basis of Le Chatelier's principle. 2H2, that's gas, O2 gas, well, let's write down at the bottom, it's gas, giving water vapor, 2H2O, gas. Now, first we're going to try addition of hydrogen, add H2. Now this is how you're going to think about application of Le Chatelier's principle and equilibrium. First assume that before you do any addition, or if you remove, before you remove anything or make any change here, assume that it was in equilibrium. So reaction in equilibrium is the happiest situation, because every reaction would eventually go to equilibrium and there'll be no more changes afterwards. So if I cause any change, like I'm adding hydrogen, that's a disturbance, that's a stress to that reaction. So if I'm adding hydrogen, it will try to get rid of that extra hydrogen because it was happy with this equilibrium concentration. So when you're adding extra hydrogen, it will try to get rid of that. It's comparable to if you have a headache, you don't want headache, and you try to get rid of that headache. So here you have adding hydrogen, extra hydrogen beyond its equilibrium value, and it would like to get rid of that. Now there are only two ways it can go, from left side to right side or from right side to left side. If it goes from left side to the right side, hydrogen will be consumed. So in other words, in order to get rid of hydrogen, it has to go predominantly this side, from reactant side to the product side. For the flow, we'd call it left to the right favored. So equilibrium would be favored from left hand side to the right hand side. B, second case. Before I go over the second case, let's consider that delta H for this reaction is negative. Negative means it's an exothermic reaction. That means heat is given off. That means as you get product, you're also getting heat. So you can consider, in case of exothermic reaction, heat as product. Now you can apply Le Chatelier's principle. So my question is, heat added, how is it going to change the equilibrium? Because that's the disturbance, you're adding extra heat. Whatever heat it had, it was quite happy with that. Now you're adding extra heat, it will try to get rid of that. So there are two ways it can go. Left to the right, just like before. If it goes from left to the right, you get more heat. So that doesn't help. But you want to reduce the heat, so it has to go from right to the left. Because going right to the left is going to consume heat, because we're considering heat as product. Consume heat and you get hydrogen and oxygen. So when heat would be added in this exothermic reaction, reaction would go from right hand side to the left hand side. Now, if this were an endothermic reaction, endothermic means heat would be like a reactant, then addition of heat would move it from left side to the right side more predominantly. Always keep in mind, whatever you are adding, it will try to decrease that. If you are removing something, it will try to make it up. For example, if I get rid of some hydrogen from the equilibrium, that means it's lost its equilibrium concentration. So it will try to make it up. How can it make it up? By going from right side to the left side. Okay, third case, say volume is doubled. Quite often students make this mistake, so let me draw it so that we can explain to you. So initially said this is the volume, and I had a piston here, I can pull it up. So I doubled the volume, so your final volume is here. When you pulled it up, let's write down here. Total volume for all the gas molecules is increased to double. Volume double means the total volume has been doubled. Initially, this is initial, and this is the final. Now, you need to, before you apply Le Chatelier's principle, you need to first think about what is happening here. When you double this volume, I made extra space. That means I can fit in more molecules. So now you can apply Le Chatelier's. Now you change the equilibrium, made extra room for extra molecules. That means you need to produce extra molecules. So think about which direction of reaction would create extra molecules. If I go from left to the right, left-hand side has 2 plus 1, 3 molecules. Right-hand side have 2 molecules. So going from left to the right, you're decreasing the number. But if I go from right to the left, I'm increasing the number. So when volume is doubled, you made extra room, reaction will be favored from right to the left-hand side. That way you make extra molecule. On the other hand, if you compress it, reduce the amount of space for molecules, some molecules will have to be used up. So that means in that situation you go from left-hand side to the right-hand side, where you decrease from 3 to 2. Each time reaction happens like this. So hope you understood Le Chatelier's principle. My next problem would be on bond order and a few rate calculations. Bond order and rate. Say I have a reactant giving me products, A giving products. Rather than giving any specific reactant, I'm just saying that A is giving me products. If this is a second order, in A, my rate expression I can write down, rate equals to a rate constant times A raised to the power 2. Because this is a second order reaction, so this exponent has to be 2. Often I ask this kind of question, if concentration is doubled, what effect would it have on the rate? With 2 squared, it would be 4 times greater. If I say that it is tripled at the same temperature, so the rate constant remains the same. If it's tripled, you'd have 3 to the power 2, 9 times faster would be the rate. So sometimes we ask this kind of question. And also, this is not bond order, this is reaction order. I have the wrong term used here. Order of reaction, reaction order and rate. This is the second order reaction. What would happen if it's a zero order reaction? If it's a zero order reaction, you can write down rate as a constant times concentration raised to the power 0. Anything raised to the power 0 is 1. So basically you get rate equals to a constant What effect would it have on A, concentration of A? If I double the concentration A or triple the concentration of A, would rate change? Answer is no, because rate is now independent of concentration. It is a zero order reaction. So make sure you keep that in mind. The other thing I need to go over would be a heterogeneous reaction. So far all the reactions we discussed are homogeneous, having all gases, but I may have heterogeneous situation. Heterogeneous equilibrium. NH4HS, solid, giving NH3 gas plus H2O, H2S gas. Now this is the reaction. Let's assume that I have Kc value of 25. I'm using some of the simpler numbers so that we can explain this. NH3 at equilibrium concentration and H2O, H2S equilibrium concentration. We need to calculate these two numbers. And no other information is given. Keep in mind, this is heterogeneous equilibrium. In heterogeneous equilibrium, when you write down equilibrium expression, you first assume that everything is homogeneous. But when I see a solid mixed with a gas or a liquid mixed with a gas, ignore the solid or ignore the liquid. And that's what we're going to do here. So first we pretend that everything is homogeneous, everything is in the form of gas. Then we're going to ignore it. That way we're not going to make mistakes. Let's do this problem. Initial. At this time we're not going to ignore anything. Initial concentration of the solid is A. You can think about solid as moles per liter. And we had nothing here, nothing here. So initially, I had no ammonia, no H2S. At equilibrium, just like one other problem that we discussed, let's assume that X amount of NH4HS would break down. So my leftover at equilibrium would be A minus X. How much ammonia I'm going to get? If X of this breaks down, you get X here, X here. If 1 breaks down, you get 1 here, 1 here. These are the coefficients. 1. Okay? So when X breaks down, you're going to get X here and X here. You have to maintain the ratio. And this is the amount that broke down. So these are my equilibrium concentration. Now let's write down Kc expression. First, pretend that this is homogeneous. So you have NH3 on the top raised to the power 1, H2S raised to the power 1 because the coefficient is 1, NH4, HS raised to the power 1. Now you apply the case here that this is a solid mixed with a gas, and we are going to ignore the solid. So now you can cross out the solid. So you'd have X times X here, which is Kc. So Kc equals to, let's write down now the value, 25 equals to X squared. So from here we can get X equals to 5. So what we'll get from here, NH3 equilibrium concentration is 5, because these are all X. H2S equilibrium is also 5. So these are my final answers to this question. So keep something in mind. Whenever any equilibrium expression is given, where there is a solid mixed with a gas or a liquid mixed with a gas, ignore the solid or ignore the liquid. Only keep those gases. So keep that in mind when you have questions like these for a heterogeneous mixture. Heterogeneous means they don't mix with each other. Two more things I wanted to talk about. If I have K equilibrium value, say Kc value, very large or very small, what would that mean? Kc, very large. What does that mean? Let's pick a number. Say Kc equals to 3.0 times 10 to the power 10. What would that mean in terms of product or reactant concentration? Kc will be defined by products on the top, reactants on the bottom. So if I have a large value of Kc, that means my product value is quite large. That means this reaction will be generating huge amount of products and almost no reactant. So you expect a large concentration of products when Kc value is large. What would happen if Kc value is small? So 3.5 times 10 to the negative 10 or negative 12. Again, going by the math, if I have a small value, that means top values are pretty small and bottom ones pretty large. That tells me if you have a small values on the top, that means I have a very small amount of product. So mostly I'll be getting reactants. Not much product would be there in this reaction. So this concludes my review session 1 for your exam 1 for Chem 112.